Well, good day, everybody. This is Bradley Needham with Developmentor. I'm going to go ahead and start the webcast now. We will be discussing lambdas in C++11 and 14. So what I wanted to discuss here is we'll start off talking about basic lambda syntax in what was added in C++11. And then after that, we'll move on and talk about some of the enhancements that were added in C++14, including some things to allow for move capture, which was actually noticed missing in the C++11 standard, but Standards Committee decided to go ahead with the way it was and then kind of enhance the model overall of capture and move into a init capture for the C++14 lambdas. All right, so let's go ahead and start in. Let's get this to the next slide here, and let's talk about what a lambda expression is. So a lambda expression itself is just that. It's an expression. And it's a shorthand syntax for creating a function object, right? And so a function object is basically a structure or a class, right, that overloads the parentheses operator, right? And that's what makes it a function object, so that it can be invoked as if it is a function, often also known as like a functor. And the lambda syntax here, the expression that you can write, allows you to create, basically declare, define, and instantiate one of these function objects in line in code. So like right at the spot where you're going to use it. So this example here, I create a lambda and I capture a copy of it, right? Basically, I'm just kind of saying auto is odd, and the compiler is going to figure out what type it is and give me a variable type. And then I can invoke it, as you can see down here, as if it is a function. So let's go ahead and look at that a little bit, what's happening here. I kind of have a vector out here, so we can do some little tests here. One of the algorithms we can use is, say, std countif, right? And countif is an algorithm that's basically just going to count according to some predicate that you pass it. And the way we do this is, we pass in our begin, v, and our end, v. And again, those could either be calling the member functions or just go ahead passing them to these global functions begin and end, which now exist with C++11. And then I want to pass the predicate. And the predicate passed here, right, could be a function object, right? Simple as going forth and creating a function object, which would be struct is odd. And a function object means that it overloads the operator parentheses. And I'm going to pass in an integer, right, is what I'm looking for. So I'm going to pass in my integer x, let's say. And then in here, I'm going to return the x modulus 2, which of course returns 1 if it's odd and 0 if it's even. And then down here, all I have to do to pass that predicate is, of course, instantiate it. All right, so there's me invoking the default constructor to create an unnamed temporary of type is odd. So in this way, the way we've done it before is like kind of the longhand syntax. So the interesting thing about lambdas is they didn't really add any new expressiveness to the language. They just made it a little bit simpler, like a shortcut to creating this kind of construct. So in this case, here I have my declaration. Then I have my definition of the function as well as the overload of the operator. I could have separated those out. And then I have the creation, basically the instantiation of the object. I have to create an object. So this is the type, and then this is the instantiation. So in Lambda terms, we basically use a preamble. Basically, it says we're going to start a lambda, and that's just the square braces, the capture clause. I'm not going to capture anything yet. We're going to show you that in a minute. And then, of course, I can just basically provide the same overload for the function here, return x modulus 2. And this does all three of the things that we did in the previous case. So let's go ahead and just print this out so we can see auto c equals, and then we can print that out. Std c out c. And when I run it, down here we get 6, and so this says that there's 6 odd numbers here. So 1, 2, 3, 4, 5, and 6. So good. The algorithm's working. So that's basic syntax for a lambda, right? And so we've seen this as C++11. We introduced this, allows us to create these functions objects a little simpler, right? So Then let's talk a little bit about what is actually generating here. And we've seen that there's a closure type, and the closure type is the kind of the hidden generated type that the compiler creates for the Lambda expression. So in this case here, when I did this, right, we have the declaration. The declaration is over here. So you can think of the compiler as generating a class just like that, right? And that's the closure type. So when you listen to the people understand or talk about the closure type, and in most cases when we're dealing with lambdas, the difference between, say, like the lambda expression, which is really just the syntax for writing the lambda, the closure type, which is the class that's generated for that lambda expression, and then the actual closure, which is basically an instance of the closure type, to really know the distinction between them isn't all that important in most cases, but there are some cases where it is important to kind of understand what's the compile time constructs, right? So the compile time constructs are the syntax itself, right? Basically the expression and the closure type, and then the runtime construct is really the closure itself, basically the instance of that closure type. Okay, so basically the closure type you can just think of as what the type of is_odd here is in this case. Okay. So then the closure, right? The closure is then, of course, the instance, which I just said, right, is the instance of the closure type, and that's what's is_odd actually is. Is_odd is a closure, and if I created another one, if I said something, down here, if I use this as, let's see, Control X, let's do something like auto is_odd. So this is a variable now, so I'm going to clear out this structure type. Is_odd equals, right, here, the lambda, right? So this is a copy of the closure that's generated here. I can even create another copy by saying, auto, function equals is_odd, and that would basically be a copy of this closure that was generated here. So I can use it again. So in a lot of cases, if you create a lambda in a particular spot, you're going to, again, like I said, it does three things in one spot. It does the define, it does the declaration, the definition, and then the instantiation. You get back a variable. You can then pass this variable around because lambdas are copyable, right? So they're copyable, and I can then use them somewhere different. Okay. All right, so what after the closure? So now let's talk a little bit about lambda capture. So in this case here, when I first created this is_odd, I didn't need any local variables or any parameters to be used inside this code. You notice that my implementation for my lambda is pretty clean. It just takes the input, which is the x that is passed in there, and then uses some other constant value. Now, if I wanted to have a particular value that would be used inside here instead of, say, 2, if I wanted to use, create something is multiple of, right, something like that, I could then, say, have some constant or some variable in the outer scope here, say something like, auto multiple. Let's call it the multiple here, and then I could say something like 3, right? Assign it to the value of 3. And then down in here in my lambda, if I want to use this value, so I want to use mult here, notice I can't use it. Let me change this here so I get rid of this error. I can't just directly use it inside this code without capturing it into this scope. And the reason why is, if you think about it, again, this is basically generating a function object. So that function object, in order for its operator to hold this value, it has to have some way of pulling it into the lambda itself, and that's what this capture block is used for. So if we go back to making this into a structure, we think about, well, what is the compiler going to generate for me in this case? We can then maybe see how it fits together a little easier. So I would say struct is multiple of, I'll just call it is mult of, and then I would have the overload of bool operator parentheses pass that in, and now you can now it's a little bit clearer why this is not known by the scope, right? If the compiler is generating this class, this type somewhere else, you can see that, oh, clearly molt is not part of that definition there, or that declaration. So how do we get that in there? So in case of a structure, a function object ourselves, what might we do? One way to do this is, of course, to provide a constructor, right, for this that then takes the molt, right, in here, the multiplier that we're going to look for, right? What is it? The multiplier is available. And we're going to have some sort of data member that's going to hold that value, right? Some sort of private data member that will initialize with the value in the constructor. So we'll add this down here as int m underbar molt. And then in this scope, which this is still missing in the scope here, right, because this is the operator overload is different, we need to use the basically the data member that we have. So we provide that in there. So this now allows me to do something as, let's kick out the lambda, and let's just put is molt of, right, and create an instance of it. This is how we do it with our own function object. And this is basically, you can think of this as being, similar to the closure type that the compiler will generate when we do this. So we go over here to the capture, and we say we want to capture the molt, right? So in this case, I just say I want to capture molt here. Oh, of course, I'm sorry, and if we're doing it by our object type, we would have to, of course, capture. This is where we put the capture block here, is in the construction of the type. So let me comment this one out, and we'll just copy and paste it so we can keep that one up on the screen for a bit. And then down here, right, if we're going to do it with the lambda, now that the capture block has captured this, right, and so then it kind of uses the same name. So we can think of it, when it captures it, as creating a data member internal to the closure type, and then initializing it with the same value that is in the outer scope, and then basically that ends up being used inside the implementation here, like this. So now I can just change this back to use is multiple of, in that case, right? So this one here is explicit capture. So I'm explicitly capturing, I'm specifying, I want to capture the multiplier here, and then I want to use it internal. So if we use the multiplier of 3, and of course we rerun and succeed, then we get 11 things that are a multiple of 3. And we're just going to assume that that's right when it comes through here. Let's see. We get the opposite. The things that we remember, we're not doing the is multiple of, because we're grabbing the things that aren't multiple of this. So if we wanted to actually turn it to the things that are multiple of 3, right, we would go ahead and do it this way, where I'd put a not in front of here. Not is mult, and then that would work better. Okay. Let's hit this back. Let's run that again. This will give us the not. So there are the multiples of 3. And there's only 2 of them. That makes more sense. There's the number 3, and there's the number 9. And those are the only 2 multiples of 3 in our expression here. Okay, so again, this is explicit capture. So if we go back to this, that's the lambda capture. And then the explicit capture basically specifies how and what to capture. And then we can also specify by reference or by value. Now, the default way of doing it is, if I specify the name here, as I did in my example of is multiple of, when I just say molt, this captures by value. And so it just has a copy of the value under here. If I wanted to actually change the value, so let's look at our example here that's given. So let's say we wanted to actually use the return result. We wanted to change for something like a for each, where it's calculating this sum of all the things that are part of here. So if I say auto sum equals 0, start that, and then I want to do a for each, stood for each. And let me make sure I include algorithm up here. I'm probably getting it already, but let's just make it clean. It's for each. And then again, just the begin of v to the end of v. All right. And then I want to pass a lambda here that does a capture and calculates the sum. So if I just did it like this, where I would say, so then my int x is in there, and I calculate, and I say sum plus equal x, the value passed in for each time in the loop. If I go here and capture sum just by saying, yeah, I want to capture sum, at the end of the run here, put this print out here and let's comment this stuff out. At the end of the run, okay, sum is still going to be equal to the same thing. And you notice that the compiler won't even let me assign sum in this case. It says you're capturing it by value, and you're also basically creating what's called the lambda itself. The operator is a constant expression, so it won't allow you to change the internal data member. So if we think about the way that lambdas are actually generated, this is closer to the way the lambdas are generated, is that the overload of operator parentheses is constant, so that then I wouldn't be able to then change this one. So if this is sum up, we change this to sum, change all these things so it looks like the generated one that's down here, sum, and change all these to msum and sum. We change this guy around, and we change the statement here, instead of returning anything, to be void, and simply say sum msum plus equal x. So this would be the generated lambda that we have down here. And you notice we're getting the same error. We're getting an error up here top that says, hey, read-only variable is not assignable. And this is the same, cannot assign to a variable captured by copy in a non-mutable lambda. And that's basically the same error because this is what's being generated here. What we really want anyway is, even if we were doing the reason why is we can't access the data members again like we can in our structure here. With the lambdas, we can't actually access the data members again. So what we want to do is, in this case, we want to capture by reference. So I specify here that I really want to capture the item by reference externally here, so the sum is passed in, capture it by reference, and then that goes ahead and changes it so that when I get to sum here at the end and I run the program, of course I have to get rid of my little generated structure there, and this one's not being used, so let's go ahead and run it again. When I run it, of course, we fortunately hopefully get the sum there is 168, and I'm not going to calculate it to figure it out. I'm going to assume that the computer's doing it correctly. Okay, so that's explicit capture, right? So you get explicit capture. Now you got to be careful with something like capturing by reference. And the reason why you need to be careful by capturing by reference is because of dangling references, and you can have dangling references. Example here, if I had a function that basically returns say a lambda, so from it comes a lambda is the return value back to me. So let's create it's the easiest way to do this function. Or actually, we'll just pass in a lambda and expect it to be copied out when it comes out. So we could have a template type name t, and then void func fun, and we will add tref lam. So this is the lambda, and then we will actually generate a lambda and pass it out. Oh no, let's not do that way. It's not going to work. It's going to get too complicated with all the template stuff here. I could create that, but I want to make it just simple to where you can see. Let's just do this. Let's say that we create a scope here. So let's create a scope, and let's create a lambda inside that scope, and we'll give ourselves a function object. So here's something. So we know that from tr1 we still have our function objects, functional, and we'll create a stud function over a void int, let's say, and then get rid of these. Let's use the sum, and let's put this in the scope here. And then they'll say something like this lambda fun so inside this scope, right? And then we pass in the fun here. And of course, sum can't be looked at. We're not going to print it out here at any rate. But what's the problem here, right? By capturing by reference, and I'm trying to make it straight, straight line of code. I mean, obviously this would be a more complicated case where you were, somehow you passed in, through a couple templates and had something pass you back out, a lambda function of some sort. Is that the scope of sum, right, is from this open curly brace to that curly brace, right? And when I pass by reference this sum, when I capture by reference this sum, notice that this lambda itself is not going to be executed until after sum is no longer part of the is no longer available. It's been out of scope, and so this is a dangling reference. This reference is invalid and can cause some sort of incorrect results, because basically whatever is on the stack where this used to be is a different value probably than 0, and so we probably won't get the correct sum value when we're actually completed if we had this print out the sums as it went along, and printed them out from here till we get to the end. So we just have to be careful with things like capture by reference. This is kind of a scary one, and you just have to be sure that that's what you want, and you make sure that in the straight line of code that you're doing it. Now, there's also something called default capture. In this case, it's much clearer to the reader of the program. We can see that, this lambda is reliant on sum being available when it's actually invoked. So what we're doing here is bad. And so you can look at that in code and say, okay, I can see that's bad. And also it's straight line here. When we did something like this, which is called the default capture mode, and the way the default capture mode works is says that any local variable or parameter that is used inside the code here, the compiler will automatically capture, and this is the policy it will use to make that capture. So in this case, it's going to capture by reference the value sum. And so, we need to be aware of that, but it's harder to see, especially if this lambda was a little bit larger, to see that it's sum that's actually being captured if you just do it by default. So this will be default, will grab you any type of variable that's internal to the code here. And this one will do it by reference, and this will do it by value. All right. So in this case, again, when we do it by value, we can't, add we get the error here because we're trying to actually manipulate the sum in this particular function. And so that's not going to make sense. But this is the default capture by value. I could also do something like default capture by value, everything except for sum, which is what I want to capture by reference, right? When you list these things, okay? And really, ultimately, all it's doing is generating that function object. It's creating a constructor that basically takes a reference to an integer for the sum, and then for any other variable that happens to be used in here, it'll basically specify it as another member, and that one will be by value. Okay? All right. Let's go back here. So that's explicit capture. And then default capture, right? So default capture is still inside the capture clause here inside the square braces, tells it what we want to get for the lambda itself. And now let's move a little bit on to C++ 14. Okay, so in C++ 11, one of the problems was that we couldn't actually move a a variable into a lambda. So we couldn't capture by move, meaning that if I had a unique putter that I wanted to have my lambda access and use and kind of pass it off to my lambda, there was no easy way to do that in C++11. There actually, and the way you would have to do it, for the easiest way to do it was to give up on lambdas and just use function objects yourself, because again, lambdas don't add any new kind of expressiveness to the language. With just a little bit more typing, sometimes a lot more typing, you can create your own structure object that overrides the operator parentheses and basically create your own lambda. You could do that and still get move capture. So when the committee saw that this wasn't available in C++11, they realized that. They thought about introducing it and thought, well, what we really need to do is we need to sit down and think about maybe there's something more than just actually adding move capture to the lambdas themselves. And instead went to kind of give this more generalized capture mechanism, which is called init capture, and actually now allows you to name the basically what the internal data member is going to be, the name of the object that's going to be used inside the Lambda code, and then initialize it in the same statement. So in the past, right, so if we looked at our same for each clause here where we were doing our sum value, in the past you had to use the same name, right? You basically, you just said sum, and it was automatically going to be initialized to the value that it found up top, to the sum value that it was going to be tied to. With C++14, you can now actually give it a different name. Now that different name is now in this scope, which is going to be used inside the Lambda, and then assign it to basically do the initialization of it inside the capture itself. So if we think about using the C++14 here, in the case for the sum, so I'm going to get this back to where it's correct and not looking for dangling references here. Okay. Let's get rid of this here. Let me do it this way. Grab this lambda, put it back here. Okay. And I'm just going to clear out all these other counts and stuff, just so that that's a little bit clearer when we're looking at the code here, not as cluttered. And get rid of this part. All right, so here's our our standard, where we did our capture. And so if we think about how our object that's created here, the function object that's created here, that's just going to be basically struct sum, and we're going to have a void operator, it's x, and then sum underbar plus equal x. And actually we'll do it like this. What I'll do is I'll make it so that it looks the same as before. Let's do it this way. Sum int s, and then sum s. Okay. And then we have to give ourselves the data member itself and sum. Right. So this is basically what's generated here with this type of capture. Now to use the init capture, you can say my sum is sum. Notice that this is no longer now captured in this scope. So this is still in the outer scope here, but this value is no longer known in the Lambda scope, because what you've done is you've given your data member the name mysum, so then it can be used in here in a separate scope. So here mysum is how this would then change. And then we could see here mysum. So this is how it would change what's actually being generated. And what's kind of interesting about this type of syntax here, the init syntax, if you think about it, is on either side of this assignment operator, the items are in two different scopes, right? So this is in the scope of the generated closure type, the closure type that's generated. And this is in the scope of, basically your outer scope of where the things are being declared and defined here. So what this allows us to do is then do, fancy things with other types. Like if I wanted to actually, pass in the entire vector to some other lambda, right? Auto fn, and I have my capture and my maybe doesn't do anything here. Maybe I want to put that whole for each internal to here into another lambda. Let's actually put this inside this lambda here. All right. Then I could capture the vector, right? But I could even capture the vector using a different name for it. So something like I could either capture it by reference, right? What we did here, we could say, my vec equals v, right? Capture it by reference. Or I could even move the vector into here and just say my vec equals std move v, and actually move the vector in here by, right? So that then when I actually leave the closure, right, the vector would no longer be utilized in here, and I'd have to capture sum as well, right? So comma sum by reference to that effect to bring it all the way down through. Okay, so this is where we can actually now, because before we weren't able to do this kind of move in a lambda itself. So this allows us to do that move in the lambda. Okay. All right. So let's go back here. Let's see where we're at. All right. Actually, before I move on to the next thing, I want to point out one thing that is sometimes, it's one of those things in lambdas that people sometimes miss, and they, don't spot it as because we don't quite understand how the captures are going. If I have another type struct, my struct, or let's call it 1 maybe, and internal to here I have a member function, right? And internal to that member function, the implementation, I want to create a lambda. So let's say I have an int size here. I'll give it some value for something. And then in here, I want to use that value in the lambda. So I say, or let's do the multiple of and use the count. So let's do the multiple of, multiple for, and let's go back and do our count. So we can say std count if, and we'll pass in a vector here, std : vector int, reference, we'll pass it by reference here, or const reference v, and then we could say count if begin v and end v, and then we can create a lambda, and in this lambda I can say, right, use our int x and put in our count, which is basically return if it is a multiple of, right? So the x is, so we put in the not here to make sure it is multiple of, is what we want, right? X modulus molt, right? And put our in curly brace here and our end semicolon. I think we're missing return molt. There we go. I think we got it clean now. Now, so what's the problem here? Here's the error, right? And the first thing we say, well, okay, well, we know what the problem is in the case that I'm not actually capturing anything, right? I'm not actually capturing molt here. So one thing that I can do is I can basically say assign like that, right? Basically put in that which does what? That says by value capture, and it's the default by value capture. The problem is this code compiles and everything, but sometimes is a little bit confusing is that we're not actually capturing molt here. And the reason that's important is if this lambda, in this case it's not a big deal, but if this lambda happens to outlive the instance of the object 1, Molt will no longer be valid because what we're capturing here is not actually this data member. What we're actually capturing is this, right? You think it's actually a this pointer, and then a this pointer, this is a dangling reference. So even though we're capturing by value, this would be a dangling reference if this lambda was able to escape this function, right? So if I returned a stood function here, and then it was invoked later on after one disappeared, this would be a problem. And this is, again, a reason why using kind of default capture is sometimes, an issue. It's sometimes you want to make it a little bit more explicit. One thing I can do is I can do that, and then you realize you're capturing this, right? The other way to make it so that it's not, if you do think, in this case it's not a big deal, right? Because we're not actually leaving the scope here. But if you do think that this lambda may outlive the scope of this particular function, then what you can do is you can actually create a local, right? So basically int local molt equals molt, right? And then you can capture the local molt here, local multiplier, instead of this. So it's just one of those things to do that. Now, again, this could be used with init capture, right? Instead of going through all these different steps to get it with C++ 14, I can also then just do this, right? And then I know that I'm going to get this value, which is the molt value, and I don't have to worry about accidentally capturing this. So this is another advantage to kind of like the init capture. And I can even do this, right? Which then also allows it to be init capture, because these are in two different scopes, right? This is in the outer scope here, which is basically a data member. This is the same as this arrow molt, and this is then in the data member of the lambda itself, and so it's basically returned here as the one inside the data member. Okay. All right. So I just wanted to, again, this is lambdas that come out of member functions. It's important to be aware of where the dangling references that you might get, and that's why if you use like a default capture mode, you might not actually identify that you're getting that you're running into that danger, okay? Because it's going to capture the this pointer, not the data member itself. All right. So let's look at the last thing here, the added thing to C++ 14. Besides the init capture, the other thing that was added into lambdas is a generic lambda. And so a generic lambda is basically a lambda which is going to use auto in its parameter list. And this is useful for, say, template functions where you don't necessarily know what the type is that's being passed in, like what the collection type is. You don't really know what the parameter is here. So let's look at a little example at that and kind of hopefully make it a little clearer in this case. So let's go and create I'm going to leave that structure there because I'm going to create it again. I'm going to just create a function here. Let's do a function template type name t, and we'll have void function, and this function will take in t, and this is actually, we can call it a call for collection, right? This is some collection that's going to be passed in. I expect it to be a collection of some sort, and we can pass it by const reference if we want as well, const ref rather than by value. And in here, I'm going to do my same. Let's say I want to do the for each, right? So let's go ahead and grab this for each here, and we can do our sum internal as well. Grab this code here, and we're going to do the begin of C, right, and the end of C. So this is some collection that's passed into us. But when the collection is passed in, I don't necessarily know what type, and actually let me do the count here because it'd be easier to do the count than also showing what type the sum has to be, because it could be a different type as well. Let's do a return long for auto. It's called call this C and call this col for collection. It changes to countif. And we're going to count it if, here are these captures. We're going to count it if return, if it's even. So let's say if it's even, we're going to say not x modulus 2. Okay. So we're count it if it's even, and then we're going to return our value c. Now coming into this template function, I've made a pretty big assumption here in assuming that the value type of collection is an int, right? If it happens to be a double, right, then it's not going to necessarily, we're saying that this type here is, and if we did something more complicated in here, I just want to point out that since this is a template function itself, right, I don't actually know at this point what the value type is. And all I really care is if the value type itself provides whatever operation is necessary down here. Okay? So in the case of, here, I don't really know what the type is. And one way to do that in the Lambda, right, is we can go back and fall back on a lot of things we know about the collections themselves. And since we know it's a collection we're going to use, we could simply put in here something like type name, the type itself, collection of value type, right? And then we know that we would get the value type, and as long as it supported that operation. But that's a lot of extra typing in here. And there's an easier way to solve it or fix it with a regular function object that we could do instead of, like, if we're using a Lambda, we kind of have to do this and fall back on some of these nested type defs here. But if we were using our own function object, right, like sum here, we wouldn't actually have to do this. So let's say I'm going to give an isEven here, and I'm going to get rid of the constructor, and I'm going to get rid of the data member, and I'm just going to have, return. Let me just copy and paste the return statement from here. Right, return statement, and so but this is a bool. So there's my isEven. Again, I'm assuming the int. How do I determine at compile time what this type actually is? Well, we just use templates, right? Instead of doing this, I say template type name t, and then I change this to a t. And now, if I wanted to use, I'm going to comment this and then put it back in so that we can see what here. If I wanted to use, say, this function object, the isEven function object, I would just say isEven and instantiate it there. And the template will this template of countif gets instantiated, it will instantiate this template, and in that template instantiation, it will determine what the value type is of this, and I don't have to type some hideous little expression here for grabbing a nested type def internal to my code. And so in C++14, they said, yeah, and that would also be very useful if we could do that with lambdas, which we can't, right? Not in C++11. So in C++14, they changed the syntax here for the lambda to allow us to basically do the same thing you're doing here. Basically, the construct that's generated, the function type that gets generated is going to be one that is the operator, the overload of operator parentheses will in itself be a template function. And the way we do that is with the auto keyword. So let's go ahead and take that out. And we change this to simply say auto. And now the generated lambda, the generated closure type looks like this, right? Gives you that templatized overload of operator parentheses, which then allows this to be correctly resolved. And then, if there exists a modulus operator that works with that type, then we will actually get the lambda correctly generated. Okay. Let's see, oops, here. So this is basically the syntax for that's happening. Okay, that is all I have for you. That was lambdas in C++ 11.14. If you have any questions, you can go ahead and let me know. And if there are no questions, then I hope you guys learned something, and I hope it was informative, and we will have some more again in the future. Thank you.